Welcome to Time Standard, a podcast where we explore the constant bending the world. This is a show about time becoming the fundamental measure of value, coordination, and progress. Tune in as we explore one of the most transformative changes humanity has ever gone through. Hey, welcome back. I'm excited to share my conversation with Giovanni Santostasi. If you are new to his work, I think a little context is helpful before we dive in. Giovanni's research immediately captured my attention because his findings were starting to make sense of a very unique behavior we see in nature that I have previously referred to as universal or generalized principles. These are relationships and behavior that transcend time and scale, meaning they are always active and consistent. They never take a day off and go on vacation. And there is a formal term for this kind of unique behavior. It's called invariance, or self-similarity. Imagine a deck of cards. Now imagine each card has a unique set of holes that are punched into it. When you spread them out, every card has a different pattern of holes. Now imagine you pick up the entire deck of cards and hold them up to the sky. To your surprise, there is one hole that lines up perfectly, and you can see right through the deck of cards. This is an example of invariance, or a universal principle. It resembles a truth that is consistent across every single card. Now you might think that was a coincidence. So you grab another deck of cards that your grandparents used to use and shuffle them into the deck. You see the same hole show up. So you buy another deck of cards the next time you travel overseas. No matter how many cards you add to the deck, from any point in time, anywhere in the world, the same hole never changes. It's remarkable. And this is how the Bitcoin network works. In Giovanni's work, he is clear that if there is one recognizable property of Bitcoin, it is its invariance. And one way this invariance reveals itself is through what you will hear Giovanni call power laws. We spend the first half of this conversation reviewing his work around power laws because it tees up another beautiful network property that Giovanni refers to as the Bitcoin growth game. History has been riddled with zero-sum games where one gains only at the expense of others. The Bitcoin network behaves completely differently. It is positive sum. And this is exactly how nature works. To truly understand the beauty of this network, we address another misconception that Bitcoin derives its value from scarcity. Bitcoin is finite, but never scarce. And this difference is not semantic. There will always be enough Bitcoin, so it is okay to use it. In fact, in this conversation, we argue that it is through this participation that the network derives value, not the supply and demand dynamics of scarcity. This is a beautiful property of the network, and I wanted to give Giovanni a little bit of space to explain it further. If you're a visual learner like me, I have a graphic demonstration at the end that might help you visualize what Giovanni is talking about. This is one of my longer conversations yet, but I think this topic deserves all of that time. Now let me get out of the way and jump into the conversation. Today, I'm excited to explore the behavior of the Bitcoin network, not so much as a financial asset, but more as a living physical system. As an architect, Dr. Giovanni's research has helped me see the beautiful geometry and architecture of the network. But before I get too far, Giovanni, thanks for being here, and can you please introduce yourself?
I am Giovanni Santostasi. I am a physicist. I have a PhD in actually astrophysics. Kind of like my colleague Stephen Perinov that you actually interviewed some time ago. But in my case, also in this case, we share these in common. I also have an eclectic career. I changed field, and at a certain point, I went to neuroscience. I opened my own company, tried to commercialize my IP in the field of neuroscience. And then I discovered Bitcoin. So I started to study Bitcoin from a scientific point of view, using the tool that I developed in my career, the same tool that were useful in understanding the stars, the universe, then applied to understand the brain, and finally to understanding financial assets, in particular Bitcoin. And there is a common theme because in many of these systems, you find similar regularities, in particular this idea of a power law, or this general concept that in physics we call scale invariance. That means that a system is similar on many different scales. And for scale, we mean big factors like 10, right? So if I see a system, I see a system means something that I'm interested in studying. Like it could be Earth, it can be a galaxy, it can be particular ecosystem. So I'm looking at this system at different point of view, from the microscopic all the way to its wholeness, and then looking at different factors of 10, almost like zooming out or zooming in. This is what we call scale. And when you do that, many times you find something very simple, that as you scale and you look at some parameter of the system, whatever it is, for example, in animals, uh, you could look at the metabolism rate of an animal and the mass of the animal, and you look at animals. In this case, it will be what you're studying is all the animals, right, as a whole. For example, mammals, right? That is your system. And when you're looking at different size animals, because that is one of the things that happen. We have many different type of animals at different sizes, and you look at the scale of the mass of the animal and the scale um, of the size of the animal. Of the metabolism of the animal, much energy the animal consumes. You see a regularity. You see that these two parameters are linearized. There is some kind of proportionality, because that is what the line means, between the scale of the energy use and the scale of the mass. Yeah, and so I found this type of behavior in all my career, and then I was very surprised to find it in Bitcoin, and I wanted to understand why, because physicists focus very much in just describing nature, but also trying to understand the causes, right? Why something happens, what is behind, what is the mechanism. And actually, we are very keen in finding similarities. Something behaves in a similar way, then in a sense, it's the same thing. We like to find these type of similarities and generalize. We call it universality in physics. Yeah, so yeah, that is a short introduction about myself.
Yeah, thank you. I forgot to mention this offline, but I was going to tell you when you first shared some of your insights, I felt like it was this Johannes Kepler moment where it's that big of a deal, the patterns you're finding in the network. And oftentimes I guess in physics, when there's a new discovery, I feel like there's often a empirical observation before you fully understand maybe and start to theorize what's going on. Is that kind of what's going on
Yeah. In
right now in
fact,
your
I was
research?
very surprised when I moved to biology. I don't know, it's something about the training, particularly in the biomedical field. We always say, oh, I have this hypothesis and I'm going to test this hypothesis, and then I do an experiment to test the hypothesis. That is not wrong, but it was like very strange for me as a physicist, because many times we do kind of almost the opposite. We collect data about something, like, for example, with Kepler, even historical, right? People collected data from on time. Now, the hypothesis could be we think there is some kind of order in the behavior, but it's such a general hypothesis. You don't make it so precise. In biology, sometimes it's very, very precise, like all these particular, if I increase this level of sugar in this animal, I'm expecting to see this particular effect. And now, then you don't see it, or maybe you see it and it does something else. So it was very strange when I went to that field and they were insisting in doing that, maybe because it's so complicated that you want to focus on something very specific and focus on that particular interactions between what you're studying. But in physics, many times we just look at the sky, look at the planets, collecting a bunch of data about the motion of the planet. This is exactly how we went. And then the general hypothesis will be, I think there is some kind of organization and some order. And then you try to figure out what this order is, right? And that happens very much in physics. Like, I eat up, like almost like children, like, big revolutions happen in physics when somebody, of course, maybe there is a history, maybe there is some reason, but, more or less was, I'm taking a piece of metal, I'm going to eat it up. And we know that it warms and it
Mhm.
needs heat, but also light, right? And I'm going to see what happened between the energy that I put in and the light that gets emitted, right? When when you see in movies, when they make a sword or whatever, right? The sword is very white initially, and then as it cools down, it becomes more reddish, right? Yellow and reddish. This how actually we know the temperature of the stars. We learn from that, and then now we know how to associate the type of light emitted by an object that is hot and the temperature of the object. This is why we know, oh, that type of star has this temperature, we can do this association because we do an experiment like that. We don't know what is going on. We just see the general phenomena, heat and light emitted by the metal. The star are not made of metal, they are made of gas, but it's a very similar process. And then we collect the data, we plot the data, we see if there is some kind of order and organization. And then later we make a model, right? That is different from actually what many people talk in when they talk about online, all this model that you are describing for Bitcoin. Actually, again, it's a kind of wrong word in how we use it. We do things in physics like I'm fitting the data. This is how you will say. It's not completely wrong. It's mathematical model, you will say, but the model in physics means more like, okay, I'm going to make a toy model of what I think the atoms are doing inside the metal and how the heat makes them behave. And then I explain why they should emit this light, because I have some kind of idea of how moving particles produce light. And I'm going to predict some kind of a function of energy versus temperature versus the frequency of light that is emitted, right? So that is what usually we say, we talk about model. That is, for example, something that we are still missing with Bitcoin, because I'm going in that direction because first, right, I found the pattern that is this power law that I described before. Basically, you take the log of the price, you take the log of the time, and you get this straight line. For many people, it seems so trivial, but it's not, because nobody ever discovered that before I did it. Also, the interpretation, it's a power law, it's a scaling behavior, it's similar to nature, similar to other nature. Even now, when I say that, many people are skeptical of, they don't understand it, they don't see the significance. For a physicist, it's so trivial and so fascinating. Me and Steven are in the process of actually writing scientific paper. We want to send it to the community. I will be very surprised if there is a rejection of this idea. It will be so familiar. Maybe if we get some pushback from a scientific literature, the scientific community will be on technicality, then can be fixed. But the general idea, yeah, it's a power law and needs to be described. It's real. It's there. And, many people in the social media debate about the details, and it's so silly. But yeah, this is what I'm trying to teach also to people, to start to think a little bit like physicists in general, but in particular because our community is very interested in Bitcoin, in understanding how Bitcoin behaves. And you were mentioning Kepler. Kepler did the same thing. Like, he tried so many things, nothing was working, and finally tried. I'm going to cheat a little bit because they didn't yet have graphs yet. That was an invention of Descartes later, but he kind of look at the data. If he could graph it, he would have been even more shocked. But logs were coming out at the time. They were not fully formed. In fact, he helped himself a little bit in defining what logs were. But he had these tables, and somehow in his head, he realized that it was some kind of proportionality between the log of the distance of the planet and the log of the time it takes the planet to go around the sun. Because at that time, they were already thinking that the correct model of the solar system was with the sun at the center and the planet moving around. And then he realized there is this very incredible regularity that everybody can do this now. You can go to ChatGPT and say, hey, ChatGPT, can you do a log plot of the distance of the planet versus the distance, the time it takes the planet to go around the sun? But it's called the orbital period, right? For the Earth is 1 year, for Mars is about 2, for Jupiter is 12, right? But ChatGPT can do that in a second because it has the data available and it can produce the chart. And you will see this beautiful line. And if you ask to give you the slope, it will be 2/3 of that slope. And that is basically saying that the distance of a planet is equal to the time it takes the planet to go around the sun, the period, to the power of 2/3, because turns out that the line is the power of this power law, because a power law means there is a power relationship, right? It's not linear, it's a linear relationship in logs. When you go through the algebra, then it turns out the underlying equation is equal y equal x to some n. In this case, the distance of the planet versus the period to the 2/3. With Bitcoin is price, time, because in this case is a time even in the period, because period is time. In this case, it's no a time that is equal for each planet, that is fixed for every planet. So it's a process in time, right? It's a growth. We are describing a growth as a power law in time. And there are power law like that are very legit. That is another thing I debate often with people that are not familiar. They say, but this is not like a power law distribution, a relationship between the frequency of some event, like, for example, how many earthquakes there are of a given size, and you can do what is called a distribution, right? So you make a plot of how many earthquakes in a given region over the earth there are of a given size. That will be your y-axis. On your x-axis, you do the size of the earthquake, and then if you take a log of these two quantity, will be a straight line. That is a distribution. But a distribution relationship like the one for Kepler, or a growth pattern. There is an article, for example, where people say, but we don't have example of that. It's not true. There is, for example, an article that shows the growth of a tooth in an animal, the growth of a shell, the growth of nails, the growth of horns, thorns. All these structures are power laws. I don't remember the title, but if you Google power law tooth, this is how usually found this article. You will come up. You will see it's a general power law for the growth of they mention all these things: tooth, nails, shells, thorns, all these structures, and then there are graphs, very clear graph of the size of, for example, the radius of a tusk of an elephant versus time, right? It is kind of what we are describing. But then there are articles, for example, that I mention often, that describe the growth of networks. And also that we are a growth in time with the size or number of nodes versus time. And yeah. And that have all power laws. The social networks grow like power laws. Yeah.
The other one that's really surprising to me is the number of words in a language.
Yeah.
Almost all of these power laws, it's almost hard to believe until you see that line.
I know.
It's unbelievable. And then you see that line, and then it makes you think.
Yeah, exactly. And then, if you go deep, so I'm writing an entire book. It's called The Physics of Bitcoin, that everybody should go and buy and read, because it's going to be a very, very cool. Actually, I'm pretty serious about this. I spent a lot of time. It's basically the summary of 12 years of work, so whenever somebody puts that amount of time in understanding something, usually there is something good, even if maybe you don't agree with everything in the book. But I cover all the relevant topics because I want to give a background to people to understand what I'm talking about. So there is a chapter on network theory explaining. So, for example, it turns out I was mentioning that when people actually went to study real network, in particular, there was this Hungarian physicist called Barabasi. He went and started to look at real network because there was some theoretical work. See, this is also what mathematicians sometimes do, right? Mathematicians, usually they make up a problem. They say, okay, I am under these conditions. These are my axioms. We don't call it an hypothesis. They start with some axioms. These are the initial condition of my problem. Then we study what could be the consequences. But that is the problem, is that in this very artificial world, and they don't go and look in nature. So it was this famous mathematician called Erdos that started to work on this very primitive, very artificial network. And one of the results was that the number of connections at every node, right? So network is made of nodes and links, right? Nodes could be people, computers, cells in a body. So basically some local structure connected through some kind of a link, some kind of communication channel with some similar structures. Cells giving information to each other, like neurons, or maybe DNA material or proteins, communicating somehow, or people in a social network, discussing with each other on a social media, or maybe computer talking to each other. Right? So this is what a network is, and this network offers much more complexity and interesting type of behavior relative to other much simpler system like a gas, right? A gas is just made of particles, they collide with each other. Still interesting to study, much more boring. The metal that I described actually is a little bit more complicated because there are quantum mechanical interactions between the particles, so it's actually more interesting. It does weird stuff that people didn't expect. This is why how quantum came about, because they couldn't understand how this light was emitted by this object. It didn't do what the theory say it was doing until they introduced ideas from quantum mechanics. It's a very interesting story. One day I'm going to write a book about the history of physics in my own way. It's really cool. It's probably the best way to study almost anything. Study the history, how people arrive to these ideas. Because it tells you a lot. How it kind of makes you also think in that way, to learn how to think in a certain way. But with Bitcoin, so the discovery came about, like in my case, by playing around, and then listening to actually Jeffrey West, and he inspired me. And then I was looking for these power laws, and I almost immediately found them. And I was telling you that will be interesting in go deeper and trying to understand, come up with a model of how the interactions are happening between people. And for example, something similar to what Barabasi was doing that I was explaining, right? So this theorist said, should be random connections. So basically, this bell curve, right? That describe heights, for example. So you take a node, it will have most of the nodes will have this number of connections. Some nodes will have many more, but as you go and look at many of these nodes with a lot of connections, so very little connections, so distribute, so how many there are of these particular number of connections, they became less and less and less very rapidly. And most of them have kind of similar type of connections. And then when they actually went, because this is what physicists do, go and get the data and see how the data looks like, that, seems obvious, but we do. They found out, these physicists found out that the real network, in particular at that time, they had the early internet. And so we had a list of all the connections, who was connected with, it was easier because there were many less connection than now. But they found very quickly that this graph where I told you, right, the number of connections versus the size of a connection in the node, it was a power law. And it needed to be explained why. The theory says we should get this bell-shaped curve, and that instead we get this straight line in the log-log graph. And the physicists are trained to realize that means there is no a particular scale. There is no place in this system where a particular connectivity is more of preferred than another one. All of them have the same validity. And yes, but it tells you that there are very few there are very few nodes with a lot of connections. But there is, it's self-similar in the sense that all the scales are represented equally in a certain sense, right? Because at least in terms of scale, right? If you describe it in terms of these changes of 10, then it looks like a straight line. That means it's and the straight line is self-similar. So there is not a preferred scale. All of them have the same type of role, and they contribute to how this system works. And this is why so many systems behave in that way, because in nature, when there are certain type of interaction, often interactions that are non-linear, like instead of summing up, they whatever interactions happens, you get some kind of multiplicative effect. Just to give you an example, I throw a rock, right? This rock hits another rock, the rock splits this. Now I have two pieces, right? And or an avalanche, right? Maybe it's easier to think of with an avalanche. There is an avalanche of maybe stones or something, right? But let the stones go, hits another stones. These stones hit two stones. These two stones are hit other two stones. These two stones multiply, right? Because every time a stone hits other two stones, maybe nearby, or maybe the stones split, right? Like, for example, what happens with atomic processes, right? The atoms split and they create so there is this chain reactions, basically. That will be a multiplicative effect. And these multiplicative effects are associated with this scale invariant behavior. Again, you will have to read the book to understand why that happens. And there are several books that discuss this at any different level. There is a very beautiful book that I keep all the time in my shelf, my desk. It is called, but it's actually signed by the author. That is my hero. His name is Back, and this book is called How Nature Works.
Yes.
And he wrote this book that is very accessible. So besides Scale by Jeffrey West, if people want to learn more, I suggest to read also this book that is The Science of Self-Organized Criticality. That is one of the topics I discuss in the book. And so, and these all these applies to Bitcoin, because what happens how Barabasi found out that a real network in life found themselves when they interact with the real constraints and limitations of a physical world, they are not behaving like these theoretical networks that this mathematician Erdos described. It was a fantasy in a sense, a very particular case. Real networks are linked to power laws. And Bitcoin is a network, And so it's not surprising to find a bunch of power laws. And so when I found the power law in price and time, that is what most people know, that again, it's price proportional to time a la 6. I wanted to know where that 6 come from. And do you remember when I told you there was a 2/3 for Kepler's, right? The distance versus the period of the planet, orbital period of the planet. When Kepler found out that he didn't have any clue where it came from, where that number came from. It was there. It was interesting. Maybe God chosen that number for whatever reason. It's regular, it's beautiful, there is order. You can use it to predict the motion of the planet. You can say when a planet will be in a particular place in the sky, all kind of stuff like that. But they didn't know the cause, right? And then 100 years later, Newton came about and was able to describe by using very powerful first principle, right? He had these what they are called the laws of motion. So he started with the laws of motion and introduced the idea of gravity as one, because he said things move, like including the planet, because there are forces. There are these forces in nature, and when an object responds to a force, it starts to do certain things. It's accelerating, it is decelerating. Otherwise, an object left it by itself, if it is at rest, it will stay at rest. If it is in linear motion, it will continue to move in linear motion forever. But if there is a force, the force is going to change the motion of the object. And that change in the case of the planets is basically a circle, because things don't go in circle unless there is a force. And that force is an attractive force. It's called gravity, works in this particular way. With basically the force becomes smaller as the distance, with the square, that makes it a power law. So it's an inverse power law. The power law in this case will be -2, because we're talking about inversely proportional. So minus means inverse. And is the square. So the force becomes smaller with the squares. If I double this, distance of a force becomes 4 times less. If I triple, it becomes 9 times less. And if you put these things together from first principle, you derive a Kepler's law. So what was observed experimentally, now it becomes a theoretical derivation. That is the apex of doing physics, when you can start with first principle, then you describe a known, very important phenomena. It's like, the apotheosis of physics. This is what we do, and this is how we do progress in understanding the universe. Now you will say, well, wait a second. Are you telling me that Newton was able to explain a power law, the Kepler's law, with another power law? Yes. But it's in a sense a development, because this power law that Newton was described, is the force of gravity, is more fundamental. It describes something that is everywhere in the universe. It applies not just to planets, it can also describe why this pen is falling down, is the same force. So now you say, look, it's this behavior of the planet is a consequence of something more fundamental. Yes, we need to understand how this works, but that is what we do next, right? But I can tell you that behavior derives from this. That is not fundamental. This is, right? So you see the progress. It's some progress, right? And it's an important progress, because that allows us to send probes to Mars, projectile, sometimes bad stuff like ballistic missiles, which are relevant right now with the war. They, believe me, they have that equation of Newton somewhere in the computer that calculates all these things and send these missiles. And so we do positive things, sometimes negative things. It depends on your angle. But this is how science works.
Is there a difference between these universal principles, invariant laws, and what you would call a natural law or a law of nature?
Yeah,
Are they kind of the same
before
thing?
before I answered the question, I was telling you that basically what Newton did with Kepler, I did with the power law, because I found the law first of all, and then
Right.
I was able to find other two power laws. Basically, I look at price versus addresses, and addresses are a proxy for adoption, because again, in the book I explain all the limitation of this approach, but it's the closest thing we have to measure how active the network is in terms of human participation, right? Because somebody needs to open these addresses, when you want to do a transfer between one wallet to another, and it has to be a human being. So the number of wallets measure the participation in the network. And it turns out that if you look at the price versus addresses, you do log of on the y-axis price, on the x-axis addresses, another beautiful straight line if you take a log. That is another power law. In that case, is square. And this is something that actually, that when you discover something like that, you're on the right track, because there is actually a theoretical result that it was not easy to verify. They kind of verified it with Facebook for some time, and turns out actually it works if you look at not the price of Facebook, but the dollars in sales, not just with Facebook, but almost all the social media platform, that there is a square relationship between in this case, let's say, how much money Facebook does and the number of people that use Facebook. And it goes with the square, because actually that is called the Metcalfe law, that was discovered by this engineer that was actually selling Ethernet cables. He invented the Ethernet cables. He was selling them, and people were not buying enough of them until he realized he could tell them that they were buying connectivity, right? People didn't realize the value of connectivity at the time, because the internet was coming out. People were not familiar with it. They thought, okay, maybe I can connect the computer with a printer. That is the usefulness of this cable, or maybe this computer with that, they communicate, but they didn't realize how valuable it is to have a network. And what Metcalfe did was to calculate the number of connections that you can have in a network. And as the network grows, it's not precise, but it's an approximation that is valid, particularly when you have a lot of nodes. It's a square of a number of links, so the connectivity is the square of a number of nodes. And then he said in a very general way, this is what he was saying to his client without proving it, because it's very difficult, right? How do I really measure the value of this network monetarily, right? It kind of makes sense. It's proportional to the connectivity, and the connectivity is a square. So it has to be the value of a network is the square, right? But then they found out with Facebook, with many social platforms, that is actually true. And it's true with Bitcoin, because the price, that is the value of the network. Now, somebody could say, well, it's the price time the market cap. But my market cap is basically constant right now. We mine almost all the Bitcoin that there are to mine. It doesn't change by a big factor. So you can say the price is the value of the network, and that price is proportional to the square of the users. That is amazing. And then it turns out that the number of users, so if you do addresses versus time, is another power law. It's a power law with the cube of time. And it's really cool because many things grow with a power law with the cube of time. Among all of them, and this is often misquoted because people say that the internet grows like an S curve. And the S curve, remember that bell curve that we mentioned, is the sum of that bell curve. It's the integration of a bell curve. So basically, imagine you have a distribution of users that is like a bell curve. I sum how many people at any moment participate according to that distribution. I get this S curve. It is kind of like an exponential initially and then saturates, right? This is why it's like a S curve. But Bitcoin doesn't follow that. It follows a power law. And that is really cool because, again, it shows, you know what, Elsa grows like a, that people say grows like an S curve, but it doesn't. The internet, that is a network by definition. The internet grows as a power law. And guess what? As a power law with the cube of time. Now, how can you tell me that is a coincidence? Do you know what else grows as the cube of time? The spread of certain viruses, in particular AIDS, for example. AIDS, and it's interesting because it's kind of a curve of distribution, because at a certain point, people were aware of it, how AIDS was contagious, and so they started to take preventive measure, etc. In fact, it turns out that any processes that could be exponential, if you have some kind of a curbing mechanism, they became power laws. And you could say, well, so you're telling me that Bitcoin is like AIDS. It's a virus. It's a virus of our mind. Also, the mechanism that a virus uses to spread in a population is very similar to the idea of Bitcoin spreading through the people, through the population, through the world. So it's very similar mechanism. That is what a physicist here. And this cube is a recurrent theme. But when I found out that, again, I was laughing like crazy because, look, square Metcalfe, cube virus spread. You put them together and you see the power law in time. You explain the power law in time with two other power laws. So, kind of what Newton did with Kepler's law, explaining a power law that is emergent with two more fundamental ones, right? Now, do we have a model why Metcalfe law works? Well, we know that it's the number of nodes, but why this type of number of nodes instead of others? How one big question that is a research question, how a price that is traded in the market knows that is a network. How when I trade, why NASDAQ that is also traded publicly is not a power law, but people can trade because in the end it's, the price is determined by price discovery in the markets, right? How do they know that is a power law? Hey guys, we need to trade it at this level, because it's all, spontaneous. It's all interactions between people. One thing that I can imagine, but we need to work on that. That is a research question that somebody needs to. And so I tried, and other people are trying to move in that direction. You can model different agents interacting. There are different type of interaction that you would not find in NASDAQ because, like, for example, people listen to this podcast and, your hub, that is one of the reasons why we have power laws in networks, because, maybe you are not one of the major hubs. Some people have millions of connections in the Bitcoin network. You have maybe thousands, but you're a hub because there are some people that have one or two connections, right? And so people listen to this to this podcast, and they say, oh, okay, maybe it's a good idea to buy more Bitcoin. Now, they get motivated. They get type of actions that you will not find with Nasdaq, because Nasdaq is all about saving or maybe speculation, etc. While with Bitcoin, people have convictions. It's a viral idea, right? People get orange peeled, right? We have even a term for that type of viral infection that we call orange peeling, like the Matrix, right? Instead of being red or blue peel, you get orange peel. Like Bitcoin is orange, is the color of Bitcoin. So, we could come up with a model that say, okay, this is why we have a price we follow a power law instead of something else, right? But we start always, and you kind of asked me that question, so it took me forever to answer the question.
No, that's interesting.
It's you start with the observation, and then you're trying to find the mechanism, right? And we are doing progress, right? Right now, we identify two mechanisms that seems very valid and very interesting and very proper, for the phenomena that we are describing, because we are network property, and it seems obvious that Bitcoin is a network. And in a certain sense, this shows that it behaves like a network. But right now we are missing all the theoretical work to show, okay, these are the precise mechanisms. The beauty with Bitcoin, we have all this data from the blockchain. And so maybe actually one could investigate the blockchain to show, yeah, it really behaves like a network in terms of how the price is expressed. So it turns out even hash rate, for example, hash rate is also power law. It's a power law that goes price to the square. So all these things interact with each other.
Hash rate to address is a particularly interesting one to me. Does that one stand out to you?
Yeah, of course, because they are all connected, right? So once you say, oh, there is a connection between price and addresses, and then price and hash rate, then there is a connection between. I made actually a diagram, it's also in the book, where I have there are 6 power laws. They are all interconnected. They are all. That is another way of getting very strong power laws, when you have a lot of feedback loops. You have these feedback loops produce a lot of these multiplicative effect that I describe, and then multiplicative effect lead to power laws. So it all makes sense. This is why I call it a theory. It's not a model. It makes me upset when people call it a model. It's not a model. It's a theory of what Bitcoin is. Part of this theory is to explain actually this observational fact that there is this linear relationship between this quantity when you look at them in a log-log graph. But the theory is trying to make sense of all these, so it goes much deeper. It's trying to find all these connections, all these mechanisms. It's trying to give also basically it's telling us what Bitcoin is. It kind of addresses all these criticisms that is just a speculation, that is it doesn't have value. There is an entire chapter in my book that I call the value triad. And the value triad is the ledger of Bitcoin that by itself scientifically could be one of the most revolutionary things ever in the world of finance. The previous revolution that is comparable is when Italians invented the double entry ledger. That changed the history of finance in the Western world. Bank where possible, insurances, all the other financial world. But it, of course, as Bitcoiners, we don't like it so much, but it had a very important role in the evolution of the Western world and civilization. And of course, we want to go beyond it. We want to make it better. But one of the way of making it better is making a 3-entry ledger, right? There is, beside what normal ledgers do, financial ledgers do, Bitcoin has these public ledgers that it can be investigated by everybody. It makes it even more honest than normal ledgers are. And so by itself, it will be an incredible, valuable thing. It will be worth billions and billions of dollars. If Satoshi patented it instead of giving it for free to humanity, he will have made billions by just the idea, of a blockchain. And patented that, people will have bought that patent and that technology for a lot of money. So when people say it doesn't have any value, it's so stupid. And then, the value of it has really that it's potentially cool. One day Bitcoin has the entire value of the entire wealth in the world. And the reason it can do that is because it can scale. One of the beautiful things about scaling is this fact that as a system scales, it slows down. So it can adapt to growth. It takes its time to go to the next stage. Every time it goes a factor of 10 up, it takes time to do that. And that allows for institutions, to adapt to this new technology and concept, to build the infrastructure. This is why we mention the growth of all these natural structures, because nature found that that is the optimal way to grow, is the most efficient and most optimal way of using resources when you want to grow something. Evolution doesn't do things at random. It chooses always the optimal way of doing something. So there is a reason why evolution follows power laws when it wants to grow something. And somehow it's so interesting that things like cities, for example, that is another contribution of the book Scales, also found an optimal way that is power laws. And Bitcoin too, that is kind of a ground up phenomena where people collaborate, work together. I know that you wanted to talk about, and we can do it for a few minutes, this, what they call the Bitcoin game, but that is where these things leads, because these phenomena that have to do with networks often have to do with things that grow from the ground up in a natural fashion, and they are not controlled by a central authority, and there is collaboration. We want to, like, for example, even the internet, right, is not competition. People join the network because other people join and they collaborate and they exchange information. We found utility in working together. Sometimes, yes, you can use the internet to do attacks, etc. But usually these are, isolated extreme behavior. The majority of people collaborate, talks, exchange information, sometimes for silly things like cat videos, but many other times for useful things. And so it's a very collaborative system. Same thing with Bitcoin. We are together, we are community. More people joining doesn't take away from anybody. And in fact, this is why, because often the other thing that, because there is also miscommunication, right? There are a lot of, we have a role, like influencers like you or even me, right? We have followers that listen to our videos or teaching, etc. But there are some influencers that give the wrong information. But sometimes, not because they are malicious, because maybe that is their understanding of this topic. And so they make an analysis. So for example, this topic of scarcity, right?
Right.
But we can discuss it very quickly, because you asked me the question, and so I need to answer. I know that I go all over the place, but
No, this is
I
great.
always go back to where I need to go. But like a Bitcoin, you were saying the question about the scaling laws and natural laws. Now, if they are laws, this is why they are called laws, right? Power laws, they are called laws, because laws in general will be it means some kind of relationship, some kind of y equals something that is kind of like a law in physics, in math. But in this case, it's really a law, because it turns out that a lot of these power laws are natural laws. They are one-to-one. I would not say all the laws are power laws, because there are other patterns. This is what a law means in physics, not like somebody wrote the law and needs to be respected. A statistical pattern that stands time, right? Like I drop a pen, I do it a million times, and there is a precise way the pen fall. But it's not always perfect, because there is noise in my instrumentation, so there is noise in the air, because there is air friction, etc. But over and over and over at time, I can average the behavior. Okay, it seems to follow this pattern. But by the way, it's also a power law, like we discussed. So, if you go under Wikipedia and you search power laws, there is like a list of 300 different patterns and phenomena, not just in nature, but also in social phenomena, finance, that follow power laws. So, I saw one time a shirt that says, I need to get a shirt, but I made a picture of it. They were selling on the internet.
We need to make it for you.
I went to a physics conference, and all what I got was a lousy power law. Because many times you go to these talks in a conference, somebody's presenting some new research, and very often there is a power law there in the talk, because they are very, very common in nature. They come all the time. Now, like I say, it would be wrong to say absolutely every single physical law it's a power law. There are other things, other type of behavior, that are not necessarily power laws. But
Are they
yeah,
often
a lot of them.
associated with like a bounded or finite system? That seems to be in physics. Systems that are bounded or finite tend to have a different kind of behavior. Not necessarily, or
It's an interesting question. And also, I could find probably there are some people that maybe physicists will scream at me saying, you're comparing, for example, the size of earthquakes and the falling of an object. Yes, we are both powers technically, but they are such a different phenomena. To me, they are the same. The equation is the same. And now we don't know, for example, if gravity has to do with some network property. There are some attempts in physics to describe nature as basically a grid of interacting nodes, and so maybe gravity comes out from these interactions in the network. We don't know, right? But often, the type of power laws, for example, that are described in these books are often systems where you have some kind of a process. Like, for example, he started describing something that for most people will seem completely irrelevant, but physicists don't work like that. We started with something very simple. We try to understand it, and then we generalize, right? And see similarity. He started with something as simple as Sandpile.
Sandpile, yeah.
Yeah, like imagine I take sand and started to collect it and make kind of like a little mountain and continue to drop little by little sand on it. The question is, most of the time it grows, and then if you ever done it, you drop a little bit of sand and then the entire thing collapses, right? Or it changes the slope, right? It doesn't continue to grow, but it collapses somehow. And the question is, what makes that collapse? So, for example, the first thing we want to characterize the behavior. So you will make a graph of, for example, the different, if you do this over and over, maybe with a machine, that drops the sand, when you take a video, then they study these things and they wanted to measure how big these avalanches that created the collapse were in comparison to how many they happen as you were dropping the sand. And it turns out they distribute like a power law, these avalanches. And then you can find similar phenomena in the brain. If you look at, firing in the brain, many times you find something like that, or like there is some kind of activity, when the activity is spread out, it looks like kind of like an avalanche. And then you can measure how many of these neurons are involved in comparison with how many of these events there are. And it turns out it's a power law. There are many phenomena like these, earthquakes, etc. And then you start to say, okay, is there something that it's a common through all these systems? One of the things you find common is that there is some kind of a boundary, like in the brain, for example, the neurons are confined inside the skull, or maybe the energy that is used is a boundary, or maybe, in this case of a Sandpile, is the fact that there is, the physical stiffness of a, there are other grains of sand there that when you add, you interact with them, so there is some kind of physical boundary. So there are some conditions like this, and these are some of the questions the physicists ask is, okay, what are the mechanisms to produce these power laws? What are similarities? What are differences and so on? But, with certain power laws, not necessarily you will have a bounded system, but the universe, if you look at, for example, how many galaxies there are, the different sizes, you find there. Like one day I saw this graph, a few days ago I posted, and it had almost everything you need to know about the universe. There were different power laws that were expressing, okay, here is the distribution of black holes in the universe. This is the dark energy. This is the weak force. This is the strong force. And they were all power laws. And so kind of they define the region where things can happen and things cannot happen. Why that is so, it's just like something that nature likes to do when it organizes itself on many, many different scales.
Yeah.
And with Bitcoin, that is a key factor because it's a phenomena that went, in terms of price, but also addresses, hash rate, all the different parameters. It went from small percentages, like, for example, price was a fraction of a dollar all the way to 100,000. So that is many, many order of magnitude. And it could have chosen to go exponential, doing this trajectory linearly. It will have taken forever, unless it was very fast linear growth, that would have been crazy. But usually when things change very fast, they could be exponential. Like, for example, Jeffrey West, in that book Scale, he studied corporations. Many corporations grow exponential. The problem with exponential, often they die because it's not the optimal way of using resource. They grow until they run out of their resources and then they die. And nature doesn't favor that. That is why we see exponentials, but often they are associated with cancer, for example. Cancer is a runaway phenomena that is exponential. So we see it, like in a nuclear explosion. But, nuclear explosion can last so far. It lasts very quickly. It ran out of all the fuel, the atomic fuel that creates the atomic explosion, and this is why it's called an explosion, but in nature, there is nuclear decay that is kind of exponential, and it can take centuries or millions of years. But it's again a decay phenomena where something is basically dying out. Like the amount of material in nuclear material in a rock, for example. But a lot of natural sustainable process are power laws. So it is interesting.
Sustainable, yeah. Well, Giovanni, you mentioned one thing where this network gets its value from.
Yeah.
And I know you're pretty adamant, and I think you've sufficiently proven it's not necessarily from scarcity or
Right.
supply and demand.
Yeah. So if you go to my Medium and you were curious about that, right? Actually, one of the few people that ever asked me in an interview to discuss it, because I thought when I came up with it, I thought, wow, this is amazing. And like, not because I thought it was a very good way of expressing my ideas on this topic.
Yes.
And then some people liked it, but many people rejected because this is a very, very controversial topic in the
Yes.
Bitcoin world. So let's talk it. Actually, people will watch your video too because it's controversial, right?
Well,
So
I think you're right, and I think you've sufficiently proven it, and I think it's a beautiful feature of the network. So I I just want you to have the opportunity to
yeah,
kind of
so
explain
let
it.
me explain. Okay, so many people that usually people say something like this, and one of the, in fact, I have been in the Bitcoin space long enough to kind of associate this idea with one precise event, that is Safe Dean Amos' publication of a Bitcoin standard. It is a great book. Everybody should read it. It's considered almost the Bible of Bitcoin. There are things I agree, things I don't agree. The main idea that I don't agree is this idea of scarcity. He calls it something like absolute scarcity or mathematical scarcity. All these, to me, it's an oxymoron, but and it doesn't apply to Bitcoin. I know what he wants to express, and many people find it so good of an idea because it's easy, at the
It's
superficial
intuitive,
level,
maybe.
right? It seems intuitive, but it actually goes to me against what Bitcoin is all about. And also, there are many criticisms. Like there are a lot of things that this is why once in a while people will say things that to a Bitcoiner seem stupid, but then it's not stupid to the people that say because they don't get it, and that by itself that will be a problem because if you want to communicate why Bitcoin is valuable to other people, and then we say scarcity, some people get it, many people don't, and then that is already a failure. But it's also to me, I think that they don't get it because even if maybe they cannot point the finger exactly to the problem, they kind of do, right? And then Bitcoiners will kind of stop and say, but this is technically not correct. They don't see the problem in communication, at least, right? So, for example, people will say, I heard this in an interview, but at first makes you laugh, right? Because I agree, it's kind of silly saying it in that way. They have kind of a point. Let me explain then why they have a point. They will say, my teeth also are very scarce. I have just 32 of them, right? Some people even lose some of them. Why they are not worth trillions of dollars, right? Like entire market cap of Bitcoin is worth. And we laugh about it. Yes, etc. But they are making a point. They are scarce. Why we don't have value? So if you just say something is valuable because it's scarce, and so people say, well, you need also the demand. All right, you need also the demand. But why there is demand in the first place? You're telling me that the value that is what creates the demand is scarcity, and then you say, well, unless you have a demand, scarcity is worthless. So you see, it's an oxymoron. It's a vicious circle, right? And many times the scarcity is manufactured, like for example with diamonds. There are a lot of diamonds. There are even artificial diamonds that are almost indistinguishable from the natural one. And there are also a lot of natural ones that are all not mined or even destroyed sometime. And the entire idea of diamond being important because girlfriends not like the diamond ring was completely artificially created, by the diamond industry, right? So we don't want to be associated with that. Like, are you creating some artificial scarcity that people then give value because somebody say that it should have value? It's silly. And then one would like to look at the math and how the system behaves. Like I just told you, the Bitcoin price is proportional to the number of people that join the network square. Where is scarcity in that equation? Nowhere. And sometimes people tell me, well, but if it was not scarce, people would not want to join the network. Not true. It's what people may be confused is that most monetary systems have a problem. At least monetary system our days. Some ancient monetary system didn't have that problem, and then when they had that problem, they became debased and they lost value. They have a fixed amount. They don't have a fixed amount of supply. The dollar, the euro, Romans at a certain point started. Like one of the reasons, for example, the Spanish Empire collapse is that they discovered so much gold that made the price of gold collapse, and all the gold we were finding, it actually was counterproductive instead of being useful. Bitcoin solves that by saying, you know what, let's make the cap fix. But it's not introducing some fake scarcity. It's saying a problem with monetary system is inflation and having a known amount of supply or issuance. I'm going to make the issuance a mathematical equation. Our days, I always say, for all practical purposes, is almost like if we didn't produce any Bitcoin at all, because basically we kind of reach the cap, the total cap. But, so even the issuance is an equation. It becomes less and less with time. So it's anti-inflationary instead of being inflationary. And it has a fixed value. And it simply solves that problem. And I made an analogy in the book. It says it's very similar to how nature works because conservation laws are very important in nature. When you create, you can go from energy to matter, for example, matter to energy. And you have always to conserve all kind of different parameters, like, for example, the charge, right? If I start with light and create two particles, let's say an electron and an anti-electron, I always do it in pairs. And the reason is because there are many other properties, but one of these is charge. I started with zero charge because light doesn't have any charge. And if I create an electron that has a negative charge, I need to create a similar particle that has positive charge. Like, for example, what is called a positron, that is the anti-electron, that is similar to electron, but with a positive charge. And so the sum of the two is zero. That is what I started with. This is a conservation law, right? With Bitcoin is the same. If I send you a coin right? I take away my coin. So it becomes almost like a negative coin. That is a weird idea for people, but for a physicist, in fact, one of the way we think about negative particle like the positron is like a hole. It's like a hole, something that is missing that it can be described in that way. In fact, the person that invented the Dirac that came up with this idea of antiparticle, he described it initially like a hole. They were like some missing thing, like a negative missing thing. And same thing with the missing coin that now is taken away from my wallet. It's a negative entry, like in a ledger. It will be a negative entry in the ledger, and now there is a positive entry in your ledger. And if we do accounting, the total it's constant, right? Maybe not zero, but it doesn't matter if it is zero or if it is constant. It doesn't change. It's conserved, and that is actually a very good property for money for many, many reasons. There is an econophysicist that I love. I actually want to explore more his work, a Russian one. He wrote an entire paper on econophysics. Econophysics is basically physics applied to economy, but some physicists were very unhappy about economical theories and they created their own branch of economy that they call econophysics. And this econophysicist wrote an article saying on money, and he makes a big deal saying money should be constant. And he explains why. He has all kind of equation explaining why it's a good property for money to be fixed. Something very cool. I mentioned to that article in my paper, in my book. And in fact, he mentioned also Bitcoin. He said Bitcoin is an example of this, and it's good money because of that. And it's good because it solves all kinds of problems, makes the ledger perfect. It makes the ledger. Now, you will always be worried if the ledger doesn't have an infinite as a changing amount of money. In particular, if it is a kind of a random thing that can happen at any time, arbitrarily by a third party, etc. With a fixed amount of money, you make the ledger perfect because everything is kept track of. You know exactly where it is, something missing out. The total sum needs to be that. It's done.
It's always accounted for. Always.
Yeah, and it makes it valuable indirectly because a ledger that has this property is very good, but not because it's scarce, because that criticism many people have that you can divide Bitcoin in many, many things. It's true that it's stupid to say, okay, I have Bitcoin, I divided in 10 pieces. Now is less valuable than the initial Bitcoin, right? Because it's like a pizza that is divided many times. People don't know how to do that argument. I say all the time, well, actually, what if as you cut the slice, all of a sudden the value of the pizza goes up instead of going down, actually, or stay the same. In fact, the value of the pizza goes up with the square of many slices you have.
Yeah.
That is counterintuitive, but that is exactly what happened with Bitcoin. So both people are wrong. The people that says the value decreases because you can divide it so many times so everybody can get a piece, and so it's not that valuable. Because you see, they are trying to attack the idea of scarcity. My answer to them, and then the people that criticize, the critics say, you're so silly because the pizza stays the same. No, it doesn't stay the same. Actually, you know what? As you divide the pizza is more valuable. And it's not Giovanni making up this stuff. Bitcoin makes up that stuff because that is exactly what happened. As people join the network, the value of the network goes up by square of the participants, you see? And this is how I made my game, basically saying, imagine the game goes more or less like this. I'm talking about an extreme situation. Imagine that instead of Bitcoin having produced a number of Bitcoins over time, let's say that the emission was all done at once, right? We were all the 21 million Bitcoins at once, and they were all in Satoshi hands. And then Satoshi say, hey guys, come and participate in this game, right? I made it like if it was a game. And now it looks like a pyramid scheme, all these things. No, because it's different. People are voluntarily deciding to share and be part of this network. It is a network where we share value. We associate value to something, That is how we associate value to everything. It's not that we are waiting for the other people. In a certain sense, we are waiting for other people to join the network, because anyway, network, a communication system, the internet, is the internet a pyramid scheme? No, but more people join the network, more valuable is the internet, because you can do more things. There are more people participating, more creativity, more opportunities, etc. It's very different. The idea is that the pyramid scheme usually goes from the top to the bottom. This goes from the bottom up. It's different. It's the opposite in a certain sense of a pyramid scheme. And so the people join because, okay, they see some value. They say it's almost like a club, right? Okay, I like this Satoshi. I like his idea. He has this ledger. It's great. I love it. And he says, look, and turns out if you do the math, it basically goes like this. You take the first person, the state of a network. So the first day there was only Satoshi. You multiply by 3. Why 3? Because of that cube that I mentioned before. And then by the number of the people in the network, in this case 1, because there is only Satoshi. And then differently from an exponential, because if we didn't have this factor that I'm mentioning right now, it will be an exponential. It will grow an exponential because there's almost like doubling of a cell that splits itself, right? It's an exponential growth. The factor that it's a characteristic of the power law is that the number of people that join goes down because, I don't know, for whatever reason, maybe the proposition becomes less interesting. And that again seems a bad thing, but actually it's good because it's good that there is not all that enthusiasm. The other way of thinking that there was a lot of enthusiasm initially, and then it starts to become, the network becomes more mature, and there is still a lot of interest. A lot of people want to join, but things slow down a little bit. They calm down a little bit. That is good. So there is decaying factor that is 1 over the age of the system. So on the first day, for example, so it goes like this, right? There is Satoshi. Satoshi is going to invite 3 people. Why 3 people? Because the formula is him multiply 3, multiply the number of people that are in the system already, 1, divided by the age of the system, 1. So 3. Okay, 3 new people. Among them, there is Alfini. I have this graph. I can share it with you. It's kind of a little bit funny. So this is Satoshi. Then I put like, if it's our North Star or whatever. And notice this, I don't know if it is possible to see, but if you zoom in and people can go and watch the graph in the article, this guy has big legs because he's Alfini. So
Alfini's calves?
Yeah, exactly. So I was trying to make a joke out of that. But, these are the 3 people that joined in the beginning. And what do they do? Well, Satoshi said, guys, let's divide the wealth among ourselves. But you guys need to come in and pay. So we divide the coin. So everybody has 1/4. But we put in the system, you are paying and investing in the system. So now these coins will be worth more by a factor that is proportional to the number of people in the network. So the 4 of us, right? And so that happens at every step. Every time people join, they are going to contribute in terms of what we are willing to pay for the coin, a price that is proportional. It's a rule. This is why we call it, again, we in physics, we like a lot of these toy models because you can write equations, you can run out simulations, and then you can see if describe like, nature, like exactly like they did with the Sandpile. Actually, when we did this experiment with Sandpile, they didn't even use a real Sandpile system. Eventually, they did that. They did it like digitally. They created a simulation of Sandpile with some very silly, simple rules. We often do these things in physics. So we can call it a game, we can call it a simulation, whatever, right? The point is that people are willing to, because it's part of the rule of the games, so we are not questioning why they do that. They pay more proportionally to the number, to the square of the people that come in the network. So the second day, how many people we are going to have? Well, remember is the number of people in the network, right now 4, times 3, but 3 is always there because it's kind of a rate of growth of a system, times So it's the number of people times 3 divided by the age of a system, right? So it's 4 times 3. The system now is 2 days old. So 12 divided by 2, 6. I add it to the 4 here. I have in total 10. So these are the people in the network after 2 days, 10. Then the third day, it will be, so I have 10 people times 3, 30, divide 3, that is 10, right? So I have 10 more added to the 10 previous, that is 20, right? So you see how it goes. So we have this multiplicative factor. So at any time, the number of people multiply themselves by this factor. And there is this Kirby mechanism that is 1 over the age of a system that allows the system to grow. It grows very fast. You see how many people are there after a few days, a lot, but it's slowing down as it grows, right? That is part of the system. And every time somebody enters, pays the square. So you can do a simulation of these. It's anybody that knows a little bit of computer science can, or you can even ask ChatGPT. I explain the game to ChatGPT and say, make me a simulation of how the price of each coin will grow with time, and also what everybody's value is, right? Because you are the trick here, differently from what happened in the real system, because not everybody is going to get as you join. We are not dividing equally the coins. Everybody gets the number of coin proportional to whatever you want to spend and buy, right? Here in this game is different. Every time you come in, you are getting a chunk that is equally divided, right? You don't decide how many coins you get. It's simply the number of total coin, that is 21 million, divided by the number of participants. But the new people are paying proportionally to the square of the people that are already there. If you play this game and you do a simulation, and like I say, it's all explained in details. You can read it to ChatGPT. You can copy and paste and say, ChatGPT, make me a simulation of a game. I think there are some graph where I show the simulation, but I can assure you, you get exactly the same equation. Like they will be perfect straight line because we are not adding noise. You could add noise, you could add some, but it's a game, so it's okay to get perfect lines. You're going to get exactly the same line. You are going to see the number of participants growing with the cube of time, the price being proportional to the square of the number of participants, and the price of Bitcoin will look exactly as it is. And I did this game to show you, tell me where the scarcity is here. There is no scarcity. People are sharing equally. Everybody gets a piece of a pie. Exactly all the criticism that people have, say, well, you can divide it, etc. But they don't realize that there is a non-linear factor. So the wealth of these people will grow linearly because the price goes up as of a square, but the people they are adding. We are sharing it in this way where everybody gets a chunk. So basically, your personal value goes up in time, but you're sharing everything. So even if you have less coins, the total value in dollars, and I know many people say, well, but I don't care about the value, all these ideological things. It doesn't matter. People care about the value of dollar. The point here is the value of a network is growing and in a nonlinear fashion, and the people, grow with cube, but okay, but the value goes with the 6, right? So the difference between how many people, how you divide the coins and how the coin value grows, it's a square. So you are having less and less coins, but the value of these coins goes faster than how much you are losing in terms of the coins. And there is in this system, there is no scarcity because everybody shares equally. It's not, is this an ideal system? Is something that we want? We don't have this. It's just a game, right? I'm just trying to explain that you could have all the behavior that we observe without scarcity. There is no place for scarcity. right? And people will still do a very valid choice to join the network because your wealth is going up. You join this network, your investment is going up, you know? So it doesn't depend on scarcity at all. It depends on participation, on people wanting to join this network because it's a valuable network. It's the place to be. Everybody wants to be. In fact, you know, because we have a certain limited amount of people that can join, a lot of people maybe want to join and they don't join, or they don't join because they don't see the value in the network, like with Bitcoin. But some people say, wow, this is very valuable, let me join. But the point is, nowhere the fact that it's scarce, that is giving value to the network. It's good, but it's finite because also this accounting or dividing the coin, because it would be very bad, right? As at a point, Satoshi say, haha, now I'm going to emit more coins and I'm going to keep all for them myself. That, that doesn't happen. So that is a protection, the fact that there is a finite amount of coin towards that kind of behavior. That is what we get with normal monetary system, that there are these third parties that decide to print, and most of the time they don't even divide, because think about it, right? The printing is not even the problem. The printing is, imagine if they printed and then they divided equally the money. It would be exactly the same thing. Nothing will change because all of a sudden everybody has exactly the same money, and the real things happen in economy when there is a differential, right? When there is more money here that can be spent to buy, there is a transmission. If everybody has the same money, and in particular, if this, let's say everybody decides to keep it, nothing changes, right? It will not be, will be anything they wanted to achieve by printing more money will not be achieved. Nothing changes, right? It's almost like imagine they decide to add a zero to all the accounts in the world, right, or in the United States. All of a sudden, Trump does some crazy decision, say, hey, by tomorrow, I ordered, by executive order, I ordered to add 10 to every bank account in the world, or in the United States. And see, I made you rich. Nobody's getting rich by that, right? Because all of a sudden, everything, all the prices, imagine that happens also with prices, with everything. Everything in the system gets 10, right? The prices of the goods, everything, right? If everything gets zeros, and nothing changes, right? It doesn't matter. So it's the same thing, right? So it is not that; it's how the money is distributed that is fundamental.
Well,
And here,
the reason I
yeah,
think this is important is because it changes the way you think about spending.
yes, yes,
You're saying this is a participatory network, right?
exactly,
It gets its value from participation. And currently there's this understanding that I need to hold. But I think
yes.
what you're saying is there's value in participating. And what's
Right. So,
really
in
interesting
fact,
is
actually, many times when you think about problems like this, right, thinking about extremes helps you to understand sometimes the problem. Other times can be misleading, but so imagine, for example, if anybody at this particular point, any time that they reach a certain number of people, everybody decides they all want to hold and they don't accept new people.
right.
Everything ends there, right? The game stops and the value doesn't go up and nothing happens. Now, when you tell this to people, everybody has kind of emotional reactions because we are not trying to understand what you are explaining. They are saying, I would never sell in any case, etc. Okay, do it. It's your choice. And this system is much more interesting. It's much more complex. The real system, but there are some people that sell, for whatever reason. And there are always incentives. That is the beauty, right? Going from a toy model to a real model, there are all these added complexity, added freedom, added interesting things, etc. But if we took an extreme case where nobody ever sold their Bitcoin, your Bitcoin will lose value very quickly. Nobody will want, and nobody can enter. So the value is in the growth of a system. In fact, that you have this system, it grows in time, and it can do more and more things. And now it's a dead system, and so the value, it's useless, right? People will not attribute value anymore. After some time, maybe people will actually leave because nothing is happening. The system is dead. So of course, in a system where there are different ways of interacting, you can hold, you can leave, you can buy more, yes, there are more ways of operating and acting in the system, but and that gives the beauty, etc. But look what happened. Doesn't matter. The system behaves exactly the same way. It's an equivalent in a certain sense. Even with this freedom of people doing whatever they think they do, selling, buying, the total result is the same. It's equivalent. Like in a physicist, you will say, actually, you know what? My game is a pretty good simplistic representation of what really happens. In a sense, we are sharing, somebody by leaving the system or selling some of their coins, because that is something that can happen, not necessarily when somebody, when we say, oh, the long-term holders are dumping, right? By the way, people have done studies on these. Usually the long-term holders dump at the tops, and the short-term holder that enter the system temporarily, and they maybe sometimes they don't even come back. They sell at the bottom. They buy at the top and sell at the bottom. It's something that they do, and people have studied that. But the equivalent is this thing where basically more and more people join, and the end result is like sharing equally among everybody. It's the same mathematical behavior in the end. Now you can look at the distribution of addresses, who has, right? Because there are all these wallets, and then you will find that it's not equally distributed. It's actually a power law. The distribution also, it's a power law. It's a famous power law that is discovered by an Italian. Like he found it everywhere in the distribution of wealth in nations, etc. It's called Pareto's law. And Bitcoin ownership follows the Pareto law. But I never was able to go from the Pareto laws and apply to these. I said, you see, I can go from the Pareto and derive the other power laws. It's an interesting power law that is there, but it seems that it's not necessary, because I could have this type of distribution that is like a uniform distribution, and then I could still see this type of power law that I observe in everything else. So it's like, and it needs to be studied, it needs to be understood, but I'm trying to free people from this idea of scarcity, because that is actually one of the strongest criticisms we have against Bitcoin. Many people associate it with bad things like diamonds or artificial scarcity. He created this artificial scarcity where Bitcoin gets its value. No, we created a network that people join, and when they join, they give value to this thing, and this thing goes up with the square of participant that is even better than just simply join something, because usually when you join something, the value goes up with the number of people that join. It doesn't go up with the square. That is a property of network, and it means that somehow the interaction between the participant is what counts. Not just the participant, it's the interaction between people. Whatever we are doing right now, by talking, discussing, thinking, we increase the value because somehow the system recognizes these transactions as important, and it does it, and how it does it is a marvel of nature. We can try to figure out all the details, but there are going to be always some simplifications. But that is a beauty, right? You see, this is why physicists are so happy about this. Say, look, it will be a mess to try to understand all the single interactions inside that a Sandpile, what happens when you actually zoom in and try to follow every single little grain. It's a mess. It's a mess. You can try to simplify and come up with some rules, but it will be such a crazy mess. But the end result is this very simple behavior. That is part of the beauty of this. It doesn't matter how the system knows that we are in a network. In the end, the final result is this very simple behavior. That is the beauty of it. And many people don't get it, but maybe by repeating, by writing a book, by participating in many podcasts, they start to get it. But they get it indirectly, because the fact that Bitcoin in the end responds in this way,
Behaving.
people respond like if it was a network, even if I do it unconsciously, you know. So even if you don't explain it, that is the end result. And
Yeah,
scarcity doesn't play a role,
I want to
like I don't
clarify
know
that
what.
point. I want to
Yeah,
clarify that point. It's this is not a theory or a concept. This is how the network is empirically behaving for its lifetime. You're
exactly,
observing.
exactly, exactly. That is the power, that is the power of science, that is the power of physics. Physicists always go back to data, say, I don't care what you think. Like Galileo, right? Galileo was saying to people, you know, I don't care about you telling me that the Earth, um, it's at the center of the universe, right? He has this very famous, we don't know if it is a legend or if it is true, but at a certain point, because, they actually they burned Giordano Bruno, that was a predecessor, that, he was more like a philosopher than a scientist, but he liked this idea of the planets going around the sun. And then he extrapolated and he said that the stars are also like the sun, and there are other planets, and maybe there are people there. He said that many other crazy things, but that is one of the crazy things he said. And the church didn't like it because it opens all kind of worms. Are these people Christians? Jesus came to Earth. Does he go also to this planet? I mean, he supposedly died just once? Did he die many times? It's crazy, right? To think about all that stuff. It's better that there is just one planet that is where people are. There are all the stars were supposed to be like big chunk of fires in the sky. There are no huge big suns. Million of times bigger than the Earth. It's crazy universe, right? So they burn it. This is how you solve a problem. Just burn. You don't solve it, right? You don't solve anything like that. But they burned it, and Galileo got scared, right? Because he didn't want to end up like that. It's, he did the right thing because I will have been stupid to die in that way. And so he had to recant. He had to go to in front of some authorities and say, "Oh, I repent. All the things I said were wrong. They, I think they allowed some circulations of his book, but he had basically to say that it was all speculation. I don't know what they made him do, but he said, that he didn't believe anymore in this theory. They were all wrong. And then supposedly when he left the building, he said this famous Italian sentence that is a pur si muove, that means, and yet it moves. Right? He was screaming at the building where the guys were after he left, and he said, pur si muove, that means, yet it moves, right? And yet it moves. So yet there are power laws. It's undeniable. There are no fictitious, there are no artifacts, like some crazy economy dudes on the internet say, because we don't know what we're talking about. Any scientist that see these lines, look, there are lines. I mean, you don't need to be a scientist. You can see there are lines. They are in front of us. All the power laws that are observed. There are lines in a log graph. There are power laws. You can measure. You can do all kinds of tests. Simple, sophisticated. It's a real phenomena, and needs to be explained. So, and once you try to explain, I invite anybody to show me how you introduce scarcity in any model of why we have these power laws. And so far, I was never able to show that, that with a finite market cap leads to power laws. I was not able to do it. And there is another, I told you, we can learn a lot by learning about history of science, history of ideas. It was a famous situation where Laplace, that was a French mathematician and physicist. He took the idea from Newton's and Kepler, and he made it much more sophisticated. He wrote all these complicated equations where he could actually describe the interactions between the planets. It was much more in depth than what was done before. And I discussed this in front of Napoleon because it became famous. So Napoleon wanted to understand his theories. I don't know how much he understood it, but Napoleon knew about enough of at that time to be a military person, you need to know mathematics, all kind of stuff like that. But in the end, again, is that a legend? Is it true? We don't know. But supposedly, he asked and say, well, I don't see God in all this theory of a universe that you have. And Laplace say, I don't need that hypothesis, So same thing here. I don't need the hypothesis of scarcity to explain how Bitcoin works. I need participation.
Mm-hmm.
I need people joining the network. People want, this spread of the virus happening in a certain way, the idea spreading to the population. But I don't, and I need this non-linear response of the price to adoption, which is basically a measure of the interaction of the people, that somehow the value is expressed as in terms of the interactions, in terms of the connections between people, and then everything is explained. And these are valuable explanations because they are linked to network theory. So if your initial hypothesis that we are dealing with a network, it needs to show network properties, we see network property, you close the loop, right? I don't say this is the end, because you can go forever deep, but find mechanism, describe all kind of things, why we deviate from it, the bubbles, all kind of different things. But nowhere is the piece of it, at least directly. Right? When some people can say, well, people will not join the network unless they were sure that their money was not diluted. Well, fine, but that is not scarcity. That is a different concept. It's not
Yeah, but
scarce.
nominally it's diluted, but your point is the purchasing power increases. So it's a
Right,
very
exactly. So in
interesting.
fact, you are right. You're right. I should even correct, because in average, right? So maybe you that are a holder, you buy and then your coins are never diluted, right? Because you hold the number of coins. But for the system, if you're thinking about the average user, and again, please get out of yourself a little bit and think of what I'm trying to describe. The average user is losing coins. It needs to be,
Right.
because it's the only possible way to have more people in the network and having a finite cap. It's actually, if there is a consequence of a finite cap, is this dilution, Otherwise, it doesn't make any sense.
Yeah,
So
it's
the average user is diluting his coins, and still his wealth is growing, because this is what happens in a network that increases its value with the square of the participants.
Yeah, it really is a form of accretive dilution in some ways.
Yeah,
It's a
yeah.
really beautiful concept. I hope people are more open to sort of thinking about this, because it's a unique feature.
And it's
I don't know
every
why it's
time I
so
mention it,
controversial.
people get crazy. They get crazy. They attack me. Some people get it little by little. So once in a while, I bring it back. I try to bring it in a different angle. I'm glad that you understand it and you even like it. Because it's, to me, it's so much more interesting than scarcity,
Yeah.
and it also addresses all these pushback by people that don't. Some people are naturally attracted, maybe because of the way they think about the world, and so actually that maybe a lot of emotions come from, well, I got Bitcoin because I liked it was scarce, and now you're telling me it's not scarce, so why should I buy? Because try to open your mind. It's good, you got in, but now try to open your mind and understand that is not scarcity, it's something else, something much better than scarcity, much better, because you
Yes,
don't need scarcity.
finite, but never scarce. It's you're
Yeah,
never gonna run out.
it's
It's
like I use this example, it's the pizza that can nourish the world. And now you can do it. And, when people say, well, I cannot feed the world by dividing a pizza in a million slices. You can, is as if as you slice the pizza, the value of a pizza goes up with the square.
hmm Or the calorie count
You
of the
can feed the
pizza
entire
goes up.
world, because
Yeah.
now this magical pizza slices can nourish many people at once, uh, or everybody can get a small little slice and they feel full. Yes, you can nourish the entire world in that way with this magical pizza. And Bitcoin, it's a magical pizza.
Yeah, and this is exactly why this is so different from anything else we've ever seen. The history's always been zero-sum games and fighting over. This is
Exactly,
completely different, and
exactly.
it's a very important, beautiful concept.
In fact, if you look at the title of the article, it says that it's not a zero-sum game. That it's not like I win, you lose. We all win. It's a win-win for everybody. Joining the network, it makes everybody win. So this is why I, I really actually hate that word scarcity, because we are moving towards a world of abundance, of
Hmm.
wealth. There are all these AI things that many people are scared, but if we do it correctly, it will bring a lot of wealth to humanity. And so everything is becoming more abundant, and people insist that Bitcoin is scarce. Like it's not. It's finite. It's a different concept. It's a conservation of money, that is a great thing. Nature likes conservation laws, uh, and you don't dilute it. In particular, again, it's not the problem. It's not a dilution. It's somebody in control of a dilution that does it in his favor. Because when they print the money, they give it to who they want. They don't give it to everybody, and they don't give it to you. They give it to banks. They give it to basically preferred agents, right? Clients of them, whoever does the printing, they give money to their clients, to their affiliates. They don't give it to us. And this is different. So I invite people to start to think in these directions, because, first of all, I really think this is a correct way to think.
Hmm.
I could be wrong in some details, etc., but it's much more correct and say that it's scarce. And some people say, well, um, it's a syntax. No, it's not syntax. I'm discussing ideas. It's just a. If it was a question of syntax, okay, it would be just it will be a very petty thing. So, don't use this word, use this word. I'm
Yeah.
saying the concept behind this word scarcity are the wrong concepts. It's not scarce. It solves some other problem. It's like it doesn't allow itself to be diluted. That is different. And the dilution, it's wrong when it's controlled by somebody else in an arbitrary fashion. Because, like we say, in theory, this system is a diluting system. You're diluting, in average, everybody's losing some coins. We need to have more participants. Where it needs to be that you're sharing. Somebody needs to share, you know?
Yes.
And yeah,
Only nominally, though. Only nominally. That's the
yeah,
key.
yeah, yeah. In a small chunk, and that chunk becomes smaller and smaller with time. But that is what allows the growth of a system. And you're not losing. Even if your chunk is diluted, you're still not losing. In fact, your value goes up.
Yeah. In fact, this is exactly how nature works, isn't it?
Exactly,
Yeah.
exactly, exactly. So I thought this article was going to be like viral, and it will change the way people think about Bitcoin forever. It will be quoted everybody anytime there is this pizza problem, of the uh, and very few people read it or even understood it. But yeah, it's fair. Maybe with time people
Yeah.
will appreciate it.
Yeah. Well, Giovanni, I didn't realize how controversial this was. So sorry to make you bring it up.
No,
But I
actually,
think,
it's good.
yeah.
I'm very happy because I'm covering all the other topics. I never covered these, and that's a very good opportunity.
Yeah, great. Well, Giovanni, I think I could talk to you for a long, long time because there's so much to dive into here. But I really do hope people give this a little bit more thought. Uh,
Yeah,
it's a beautiful idea. You kind of have to suspend that idea of scarcity being
and if
the
you don't like it, tell me why. Don't
yeah
say, oh, just play the game with me, and tell me, oh, there is a problem here, or maybe this will not work. That is how you do it. Just don't react in an emotional manner. Just play the game and tell me, first of all, what is wrong with the game, and second, why is not a good analogy of Bitcoin. Because I really think, even if it looks so different from how Bitcoin behaves, is basically in math we will say an isomorphism. It's one to one. is different. You are rearranging the pieces, but basically it's exactly what is happening indirectly. It's kind of like that. It's really a good representation of what kind of is happening. It's a simplification, but kind of has the same final behavior.
Yeah, to be clear, you've simplified it a little bit and gamified it just so people can understand. But
Right,
it's
exactly.
fundamentally how
and
it's
it's something
working.
that we do often. Like, go and read the original work of the author of the book that I mentioned, this book, right, of Our Nature Works. That was the seminal work because he showed that this Sandpile, but the Sandpile actually were, you know what, if people were really to learn and go deep on this, go and look at Veritasium. He has a recent video, I think it came up maybe a few months ago, and you will find it because it talks about forest fires, etc. I don't remember the title. Maybe I can give you, and you can put it in the video as a reference.
Yeah.
And it's an entire episode on power laws and self-critical system, and he talks about this. They even have a simulation. And the initial Sandpile experiment was actually on a computer. It was kind of a game like this, where there were like 4 squares that represented the sand, and you were dropping randomly grains of sand. They were like little cubes. And you came up with some rules, like if you had more than 3 grain of sands on top of each other, there will be a collapse, and then they will distribute randomly around. And so basically created like a game, something that you could play on a computer. And it showed that the distribution of these avalanches was a power law. And then he said, wow, something so simple can create this complex behavior that we see in nature everywhere. What does it mean? And, that led to probably thousands of papers that people wrote, different experiments that people did with simple system, other type of simulations. They found this behavior in forest fires, neurons in the brain, everywhere. And many times in physics, we do these little games. I call it a game. You could call it a simulation, or a toy model. Sometimes we use this word toy model. And this is a good toy model of how Bitcoin distribution works and what is the end result. And it produces these power laws. And there is nowhere scarcity beside, the fact that there are finite number of coins and we divide it, but it's not a necessary feature. You could have even the small growth of the coins. If you are distributed equally, it will be the same result. But it works much easier because we have these coins and we distribute. But it's not like doesn't appear directly in how the system behaves. It's an indirect feature that simplify how the coins are distributed.
Yeah, well, Giovanni, one thing I appreciate about your work is you're always listening to the network. I think I've heard you say, these aren't my power laws; these are the Bitcoin power laws. And almost every week you're listening and finding something new that Bitcoin's trying to tell us. So I appreciate that approach of yours.
Thank you. It's my pleasure. It's a great adventure.
Yeah. So maybe in closing here, I do want to point out a couple things. Obviously the physics of Bitcoin, unless you're a physicist, can maybe be a little bit intimidating. But I think Giovanni and Steven in their weekly physics of Bitcoin do a really good job of breaking down some of these harder concepts. You guys are pretty patient, and I would encourage people to tune in, maybe just listen in, and eventually these ideas will start to click. If you have to, maybe even start at the beginning. There's some good old videos of yours. And additionally, Giovanni's
and
new book.
If I could take, the new book, and if you don't mind, very quickly, I want also to mention the Scientific Bitcoin Institute.
Oh, yes,
maybe another time we can invite me and Steven, and we can go more in depth. The both of us can be interviewed at the same time. But it's an initiative I ask people to stay tuned because you will hear more. But basically, we are trying to extend this effort that me and Steven are doing as individual to like teams of people that are going to study Bitcoin scientifically, are going to have a physical location, a website, it's going to be a hub of scientific research for Bitcoin.
Do you know where that hub's going to be currently, or are you still figuring that out?
So physically, yes, we have actually a place in Italy, in Torino. There is a sponsor that is actually building actually a hub for Bitcoin. It's like a 5-story building in the center of Torino, one of the main squares of Torino, this large city in northern Italy. And there's going to be the education center, where people can go. There's going to be a workspace, but the institute is going to have an office where, like a physical office, where people can come and visit. But we are going to have also students. We are going to have active collaborations with local university, with international university. Yeah. So this is, and eventually we will have probably centers in many places in the world, in the United States, in Asia. But right now we start with this location in Italy.
Great, great. Well, yeah, I would love to take you up on that offer sometime. Maybe have you and Stephen together
Yeah.
as soon as you kind of have some new things to share. It's super fascinating for me. It's the most interesting framework for the Bitcoin networks. Trying to study it through this lens, not necessarily ignoring the financial aspect of it, but it really feels like a living system, more of a living physical system than a financial asset in many ways. So.
Yes.
I appreciate you sharing this approach to your work. Maybe we can call it there for now. Anything else on your way out? I'll include a couple different links.
No, thank you so much for everybody that tuned in. I know it's a lot of ideas and a lot of concepts, but hopefully you can appreciate some of it. And this is how you learn, by being exposed little by little to ideas. Sometime, many times, until things click. And I really think that this angle is beautiful, but also true, and the two things go together. And Bitcoin is about truth and beauty is Bitcoin.
Yeah, often if it's beautiful, it's true. Not always, but often.
Correct.
I appreciate it.
Bitcoin, that is the case.
Yes.
Yeah.
All right. Thank you, Giovanni. We'll be in touch.
My pleasure. Bye.
Bye.
All right. Well, that's the end of our conversation. If you understood all of that, great. But it can be a little bit counterintuitive. So I did want to spend a little bit of time at the end with a visual recap. The reason I said this changes the way we think about spending is that Bitcoin is showing us that real wealth is cumulative. So while you can spend fiat currencies like the dollar, you can't technically spend Bitcoin because the act of using it in turn increases your purchasing power. Spending implies that the amount of something decreases as you use it. I think using Bitcoin is more accurate than spending Bitcoin. Let me try another analogy. Electric vehicles have a feature called regenerative braking. Every time you use the brakes, it charges the car. It's almost like we're all going downhill, and every time you tap your brakes, it charges the vehicle, and your range increases. In other words, the more you tap your brakes, the more you can brake into the future. As opposed to the existing fiat system, you can only tap your brakes so many times before your brake pads run out. And just the idea of that is stressful. And that's part of the anxiety we all feel in the existing system. When you spend your money, you feel further and further behind. So the universal principles that Giovanni is describing have always been there, just like the gravity acting on the car. But we had no way to experience it until Satoshi designed the vehicle. So let me see if I can help visualize that a bit, at the risk of confusing you further. This may look a little bit different from the triangle or pyramid that Giovanni walked through, but it's essentially making the same point. And Buckminster Fuller called this concept multiplication by division. You might have also heard the term like accretive dilution. They're all very similar, if not the same concept. So let me walk you through a couple rules here. Like Giovanni described, this has been gamified a little bit. He called it a toy game or a simulation. I could call it a demonstration. But for the sake of simplicity, I've simplified this to show 100 participants. And all Bitcoin is issued at the beginning. It's a finite supply cap, and there's equal distribution as new participants enter. So this ignores things like the issuance schedule, but it helps isolate a few concepts. The main thing I want to show is the size of the pie increasing as the percentage of holding decreases. So here on the left, I have a pie chart, and I have two sliders, one representing the participants here that go from 1 to 100 on the right. And you'll notice as I drag this is simulating new participants entering the network. And you'll notice the slider above is the average individual holding. So because we have a finite supply, these things are correlated. So as participants increase, the average individual holding necessarily decreases, assuming that the one participant at the beginning holds 100% of the supply, which is the case in this little gamified experiment we have here. So let's just walk through this a bit. One participant owning 100% of the supply, and there's a value shown here as 1. Now this could be $1, $1 million, 1 whatever, but as you go to 2, the value increases to 4. 2 participants split the total value, so the value per participant has increased to 2. So the orange number you see here is the value of the individual holding, and the purple value is the network value. So what's really unique and counterintuitive here is that the percentage slice decreases, right, as more participants enter, but the size of the pie actually grows. And that's kind of the counterintuitive part. And what I would really like to show is this at an accurate scale, but it would fly off the page because the size increases so quickly. So what I had to do is show this purple value index. You'll notice how significantly that increases. And here's a couple, I guess we could click through a couple key relationships. So here's 2 participants splitting 50-50. Value of the network at 4. Let's say 4 participants, value 16. 10 participants, total value 100. Individual value per participant is 10. So here we're showing that your holdings as an individual or participant is actually going down, but the value of that remaining holding is increasing significantly. And I guess we could go to the end here. Say it's fully saturated, 100 participants. Each participant is holding 1%, but look at the total index value and the individual value. So again, imagine this pie is contained on this screen, but in reality, if I was going to show this at a accurate scale, that sliver would be flying off the page. So just picture this representing your purchasing power. You have this tiny little dot to begin with, and that purchasing power is drastically increasing. The shape of it's changing here because it's getting fractionalized, but the scale of it is drastically increasing. And so that's the counterintuitive part a little bit. And for me, it's helpful to visualize it in this way. It might have raised more questions than it answered for you, but the main thing I wanted to show is that the size of the pie increases as the percentage of holding decreases. So I'm not saying go out and spend everything. I'm also not saying, you must use it now if you're focused on stacking. I just wanted to show that this network behaves very differently from the existing system we're used to. So I don't know, did this help? Did it confuse you further? I'd love to hear what you think. And if I got anything wrong, I'd be happy to correct it. But for me, this is a really helpful way to visualize some of the things Giovanni was talking about in our conversation. All right, thanks. See you next time.